Hi everyone and welcome. Today we will be talking about how we enabled multi-user workflows for Kubeflow pipelines. Let's get started. First of all, let us introduce ourselves. My name is Yannis and I'm a software engineer at Arrikto working on Kubeflow. I am presenting together with Yuan Gong from Google, who works on Kubeflow pipelines. Together, we worked on designing and delivering multi-user support for Kubeflow pipelines. In this talk, we will explore how multiple users can work together on Kubeflow pipelines in a secure, isolated manner. This completes the Kubeflow pipelines experience, which allows you to simplify user onboarding with the Kubeflow pipelines intuitive UX, accelerate pipeline development by writing pipelines as Python code, and collaborate in a secure and isolated manner. So let's start at the beginning. What is Kubeflow? Kubeflow is a machine learning platform built on top of Kubernetes, dedicated to making deployments of machine learning workflows simple, portable, and scalable. Now then, what's Kubeflow Pipelines? Kubeflow Pipelines is a cornerstone of the Kubeflow platform. It provides a powerful platform to run machine learning pipelines on. It comes with a powerful UI, an idiomatic Python SDK to define pipelines as code, rich visualizations, lineage tracking, and more. So, as we said, Kubeflow pipelines are a very important component of the Kubeflow platform. However, when admins try to bring pipelines to their users, they quickly stumble upon the problem that Kubeflow pipelines has no isolation, authentication, or authorization. All pipelines are running in one namespace, one shared environment, which means that secret and data isolation is impossible. How are we going to isolate, authenticate, and authorize to the Kubeflow Pipelines API? Kubeflow Pipelines is not a Kubernetes-native API. It is not based on CRDs or an aggregated API server. Instead, Kubeflow Pipelines has its own API server and database, MySQL and an object store. In the initial Kubeflow Pipelines design, there is no mention of isolation, authentication, or authorization. So how can we extend the initial design to enable multiple users to work together in a secure, isolated manner? To design how to isolate, authenticate, and authorize for the Kubeflow Pipelines API, we first turn our attention to the Kubernetes API for inspiration. For isolation, Kubernetes uses namespaces. Almost every resource lives in a namespace. For authentication, the Kubernetes API server supports multiple methods, like authenticating users via OIDC, that is OpenID Connect, authenticating machine accounts via service account tokens, or getting the user identity from HTTP headers set by a trusted proxy. Finally, for authorization, Kubernetes uses role-based access control or RBAC for short. Permissions are defined as roles and given to subjects via role bindings. Now let's see how we can apply those principles for designing isolation, authentication, and authorization for the Kubeflow Pipelines API. First of all, let's talk about isolation. Kubeflow Pipeline's initial design has no isolation primitive whatsoever. All pipeline runs are shared and everyone can access them. We introduced the namespace as an isolation primitive, same as Kubernetes. In the Kubeflow Pipelines data model, there are pipeline definitions and pipeline runs, which are instantiations of those definitions. All pipeline runs reside inside of an experiment. Now, to extend the Kubeflow Pipelines data model with an isolation primitive, we add a namespace attribute to experiments. Pipeline runs find their experiment by looking up. Pipeline runs find their namespace by looking up their experiment. In addition, the experiment API endpoints are extended. All API calls must now specify namespace, same as Kubernetes APIs. Then let's talk about authentication. As we saw, the Kubernetes API server supports various ways of authentication. We want to support that in the Pipelines API server as well. We want to be able to authenticate users as well as service accounts. So we designed the following ways of authentication. First of all, a user can authenticate with OIDC at the istio gateway provided by Kubeflow, and then authenticate to the Pipelines API server via HTTP headers. Here, the istio gateway acts as a trusted authentication proxy. For machine authentication, istio MTLS is a good solution. but it can't easily be used with all kinds of workflows. For example, run-to-completion workloads like Argo workflows and Kubernetes jobs don't fully support running with an istio sidecar. For that reason, we also designed a third way of authentication with a service account token. Now be careful. We use service account tokens with a custom audience issued by the Token Request API. These tokens are only usable at the Pipelines API server and not the Kubernetes API server. And as Joe Bida will tell you, handing a service account token, an unbound service account token, to anything other than the Kubernetes API server is a very, very bad idea. Now we saw what we did about isolation, authentication. Now let's talk about authorization. Authorization is all about answering the question of, can user do action on a resource in namespace? For example, can Sarah list pods in namespace Kubeflow? In the first implementation, Kubeflow pipelines are using the Kubeflow Access Management Service, or KFAM for short, to authorize requests. KFAM is introducing a simple view, edit, admin, access control list abstraction for all actions on top of Kubernetes RBAC. As you can see from the permission table below, there are only 3 levels of access available, so an admin can specify a more fine-grained policy, like a user can view and create pipeline definitions but not start pipeline runs. This method is deprecated and will be superseded by RBAC and subject access review. After talking about the current way of doing authorization, let's also see where we want to go. The end goal for authorization is to map every Kubeflow Pipelines API endpoint to an RBAC permission. For example, we get the API's v1 beta 1 runs ID API call to get runs, and so on. The information about permissions lives in Kubernetes roles and role bindings, just like with native Kubernetes resources. Then permissions are checked using a subject access review call. Now, be careful and make sure to note that these resources are not CRDs, but we can use the subject access review API to authorize them anyway. So we are essentially using Kubernetes as an authorization system, an authorization database, and enable admins to assign fine-grained permissions in the same way they do for Kubernetes-native APIs with roles and role bindings. This method of authorization will be implemented by Arrikto. So we designed authentication, authorization, and isolation for the Kubeflow Pipelines service. Isolation is achieved using namespaces, same as Kubernetes. For authentication, we support multiple ways for both human and machine accounts. For authorization, we want to move to using native Kubernetes RBAC permissions and subject access review. Now, let's see how it all comes together. A user logs in at the istio gateway and is authenticated. Then the istio gateway will proxy the request with the user's identity in HTTP headers. When inside a workload with no human interaction, for example a Jupyter notebook, we can authenticate in 2 ways. We can authenticate with a service account token with a custom audience issued with a token request API call. After issuing the token, we send it via the authorization bearer header in HTTP requests to the Pipelines API server. Finally, we can authenticate via istio MTLS if that's available for our workload. Finally, the Pipelines API server, now that it knows who the user is and what the user wants to do, will ask the simple question of, can user do action on a resource in namespace? And issue a subject access review call to authorize the request. Depending on the answer of the authorization decision, the Pipelines API server will then execute an action on its database. So all in all, we explore the Kubernetes design for isolation, authentication, and authorization, and used it as a guide for the Kubeflow Pipelines API. We isolate using namespaces, authenticate using OIDC service account tokens or istio MTLS, and authorize with Kubernetes RBAC. For the next part of the talk, I will hand it over to Yuan, who will be talking about isolating visualizations, networking, implementation considerations, and more.
So thanks, Yannis. This is Yuan at Google Cloud working on Kubeflow Pipelines. Yannis just introduced 3 ways people may authenticate, but for the current phase, we have only designed and implemented using authentication info as an HTTP header. Now that the KFP API server takes a plain text header for user identity. It sounds dangerous, right? So how do we make sure clients cannot pretend to be others by faking a request? This is where istio mutual TLS comes into the play. You probably know that, so here's a really simplified explanation. First, we have a client talking to a server through plain text HTTP. After turning on mutual TLS, the request is proxied through an istio sidecar in a client pod. Then the client sidecar knows how to secure the connection to the server sidecar. And the server sidecar talks to server container in HTTP again. In this way, the client container and server container are still talking in plain text HTTP, but the connection between pods are secured and by this mutual TLS. Amazing, isn't that? So in addition to that, the server sidecar now knows an identity of clients talking to it. Therefore, we can configure some authorization rules like only allow requests from this namespace or like these service accounts. So with these istio features, we are able to set up a set of security rules to first allow traffic from istio gateway to KFP UI, allow traffic among all KFP components, allow traffic from KFP to dependent services, and the most important one being denying traffic from non-KFP sources to KFP internal components. So finally, with all of this, when KFP API server receives a request, we can be sure it's coming from the trusted istio gateway. So it took us a lot of efforts just to securely pass the user identity to our API server. That's unfortunately just the beginning of this story. The API server also needs to support multi-user separation. Think about the generic problem of adding user separation to a service. There are typically 2 options to do this. The centralized option is to build a service that takes, for example here, namespace as a primitive concept and enforces authorization rules on it. It takes more efforts to implement because we have to do intrusive logic changes throughout the application. Basically, we need to add a namespace argument, authorization, and application logic to every API method. And don't forget DB schema migration too. On the other hand, the decentralized option is to start independent instances of the original service for each user. Then we need a gateway in front of it, and we need a controller that auto sets up the services in new user namespaces. This option is non-intrusive. We're just composing existing application instances in a way that they look like a single service with multi-user support. So for KFP API server, we decided to build a centralized one that takes namespace as previously described. So a single instance means lower operational and computational cost. This is important especially because usually a platform team can handle KFP systems operations like upgrade or backup, so data scientist teams can focus on their own work. Some other reasons including reserving the possibility of building cross namespace features like sharing. And this comes with a cost, but it's a cost only for us. We did a lot of code changes through all APIs, made the namespace parameter a primitive concept, and added authorizations in place. Also remember KFP provides end-to-end reusable machine learning workflow. So it looks like this, seeing visualization right inside KFP UI. We also provide TensorBoard self-service instances and artifact preview right inside UI. However, users may decide to store their artifacts in external storages like Google Cloud Storage. So KFP UI server needs to fetch these artifacts for them in order to show them on the UI. So how do we separate KFP UI permissions? For this case, we decided to take the decentralized option here because these artifacts, TensorBoard, and visualization services are stateless, lightweight clients. So there's not much operational cost anyway. Also, users are free to configure their own instances with correct permissions in this way. Additionally, one contributor is adding volume support for data passing. A decentralized fetcher servers can even support mounting persistence volumes because they are also in user namespaces. So comparing to KFP API server, we took a different approach for artifact servers because they have different characteristics and trade-offs that in the end, both different options make sense for different things we are considering. So it's interesting that we got the experience of building multi-user support with both options for different components in KFP. There are still some missing pieces for this design. First, how do we integrate other two types of authentication methods with in-cluster traffic authorization? They can allow other workloads in the cluster to authenticate to KFP API server. Second, pipeline definitions are still shared. That basically means pipeline code is shared. So this is okay for some organizations, but not others. Then menu object store and machine learning metadata DB are dependencies of KFP. They don't support separation themselves, so it's still an open question how KFP can support separation for them. So after discussing all about the design, let me share interesting things I learned when implementing this feature. For some background, I was learning istio from the beginning through this. So I hope these experiences can help someone who's listening too. And disclaimer, I was working with istio 1.1, which was a fairly old version Kubeflow was using. It's likely some of these have been improved without my notice. Okay, so let's start. Lessons I learned the hard way. Before using any istio features, clients and servers need to have istio sidecars injected. That became my immediate blocker right away. Remember, Kubeflow is a platform of machine learning applications on cloud. There are a lot of applications other than Kubeflow Pipelines in the same control plane namespace. Pipelines was actually the first applications to require istio security in this namespace. So I had to turn istio sidecar injection on. So there are several things that can configure it. There's a cluster scoped config map that changes whether pods are injected by default. There's also a namespace label that is required before any auto injection can happen in the namespace. Of course, there's also a pod level annotation that works for just the pods. So in order to turn on istio sidecar injection, what I wanted was that all pods in the shared namespace should default to not inject, while the KFP pods can use pod level annotations to turn on injection. But that's actually not feasible because the default policy is a cluster scoped configuration, while other namespaces in Kubeflow have already been depending on that behavior. It would be a bigger problem if I wanted to change the cluster scoped default value. So in the end, I had to add the disable injection annotation to every other pod in the shared namespace with a really huge pull request. And got some really hard time troubleshooting all the pre-submit tests. But it was necessary, and it was a great step for the entire Kubeflow community to move towards integrating more istio security features. So when gradually migrating to istio, at first I was tempted to first set up some authorization rules without turning on mutual TLS. Because who knows, the documentation looks complex for mutual TLS, and so I thought probably I could skip it. But please be careful. That wouldn't work for many authorization rules, because a rule that refers to even-only namespaces requires mutual TLS. Istio doesn't magically know the namespace of a request. When mutual TLS is on, istio sidecars mutually authenticate each other, so they know each other's identity. For example, service account A in namespace B. So that's why istio can authorize requests by namespace. To put it in another way, this is actually, listen carefully, this is actually a life takeaway. So before giving anyone money, don't forget authentication. You need to ask them prove who they are first. This is as important as authorization. So these were just showcases of the hard problems that took me, an istio learner, really a few days to figure out troubleshooting. So my takeaways are, do not skip the basics. Really, understanding istio concepts save more time later. And it's good to learn troubleshooting techniques for istio system end-to-end. There's a great documentation for that. But from my experience, most authorization problems can be solved with just one section in the huge troubleshooting doc. That's the ensuring proxies enforced policies correctly section. It tells you how to enable debugging logging for a sidecar. Then you can observe what information is still parsed from a request and whether it was denied. So at the end, remember that this couldn't happen without these amazing people. We all worked on the design together while Ning, Chen, and I at Google Cloud implemented current features. Thank you.
Let's proceed with our demo. In this demo, we will see two Kubeflow users working on the same Kubeflow Pipelines installation. Orpheus and Eurydice are two users of Kubeflow who are working on the same Kubeflow Pipelines installation, but as you will see, the resources are isolated. Let's see what happens. First of all, Orpheus will log into Kubeflow. When Orpheus logs in, he will be greeted by the Kubeflow Central dashboard, where he will navigate to the Notebooks page and start a new notebook server. Here, Orpheus is using the CodeLab tutorial, the Titanic CodeLab tutorial. Orpheus will also select the Allow Access to Kubeflow Pipelines and Allow Access to Raw Configurations, which add specific service account tokens to the pod in order to access the Pipelines API server and the Rock API server. When the notebook server is ready, Orpheus will connect to it and open the Jupyter notebook he has prepared beforehand. Now, in order to convert the Jupyter notebook to a Kubeflow pipeline, Orpheus will be using the Kale tool. With the Kale tool, you can just tag your notebook cells, and with the click of a button, Kale will parse your Jupyter notebook and convert it into a Kubeflow pipeline. As we can see here, Kale converts the notebook, submits the pipeline to the Pipelines API server, and will finally present Orpheus with a link so he can track the progress. Orpheus visits that link, and here he can track the progress of his run. Now let's go to the other user. Eurydice also goes to the Kubeflow page and logs in. After that, URIDICE will list all pipeline runs, and as you can see, she cannot see the runs which Orpheus have started. These runs are in namespace Kubeflow Orpheus, while she is working in namespace Kubeflow URIDICE. When she tries to visit the link for one of Orpheus's runs, she gets an error because she's not allowed to do that. And when going to the experiments page, you can see that she cannot see Orpheus's Titanic experiment as well. To prove that, we can list the pods for the namespace of Orpheus, called Kubeflow Orpheus, and see that all the run pods are there, while in Kubeflow URIDICE, no pods exist. And this is how we isolate Kubeflow pipelines for multiple users.